Okay, the last speaker of this session is Professor Yalchin Efendiev from Texas A&M University. And Professor Efendiev obtained his bachelor degree from Department of Applied Mathematics, Moscow State University in 1993. And then he went to State and obtained his PhD from Caltech in 1999 under Tom Ho, if that's correct. And he had been awarded, he got an award in 2010 from Humboldt Foundation. The award title is Fraunhofer Basel Award. And now he's a chair professor, Mobile Chair in Computational Science from Texas A&M University. And the title of his talk is Multiscale Model Reduction with Generalized Multiscale Finite Element Method. Please.
Thank you, and thank you very much. So I will talk about some of the recent work we do on local multiscale model reduction. And we propose this new framework which will explain what's a local multiscale model reduction they have. So I will start with the introduction, and I particularly start showing some multiscale problem that we're interested, particularly what type of heterogeneities that we have. So we actually the problems that I'm interested, the problem that we're interested in multiscale, that usually have a very, very heterogeneous, complex features and high contrast. What I mean by this, that for example here I have put a couple of pictures coming from the subsurface. This is a rock at different resolution. This is at the pore, at a grain resolution, at a little larger and much larger resolution. And if you look at these pictures, you can see that the heterogeneities are very complex. You have fine features that go across little blobs here and there. And such features you can also observe as you go at the coarser resolution. Similarly, for example, in this fractured rock, you can also see that the fractures can have a complex, can be complex. And what is specific that these fractures typically have very high conductivity. In other words, the conductivity can be higher than the small scale itself, which is what we refer to high contrast. And similar thing actually arises in different porous media application. For example, here we have a filter, or the application which we're currently interested quite a bit is a shale, gas flowing shale formation. So shale is another rock that is very tight. It has a very small pores. This is at the micrometer, and these pores actually consist of two. They consist of something called organic pore, where the gas sits, absorb gas, and inorganic pore, where they absorb gas usually when it goes out and can flow. And to produce it from such rocks, usually these rocks get fractured so that the gas can go out. And when you put the fractures on top, they basically are very, very small features that is very, very difficult to solve with the standard method. So such problems in subsurface and many other porous media applications are difficult to solve, because we have to resolve all the small scale. This gives a very, very large computational problem. And for this reason, we'd like to develop some type of a reduced models. Particularly, we're interested when this problem is solved, for example, many times for inverse problem, for say uncertainty quantification and so on. So I will start actually just give briefly a few simple examples of multiscale functions. So here's what's a simple multiscale function, which I have two scale. It's a 2 plus x sine x over epsilon. I take epsilon to be 0.01, so you can see this function basically varies at two scales, at epsilon, which is 0.01. This is this wiggles, and a scale 1, which is this height, this trend that is order 1. I can take many of these features and add together with some different A's and R's, so that, say, finite number. You can see that another oscillator function, so function oscillate at a very small scale, Ri epsilon, so there are many of them. If I go a little bit more complex, this is a more general heterogeneity that I'm interested in this talk. So here, basically, black means, say, low values of the field, and white means high values. So if you look at this field, you can see many, many scales. And the way you can observe many scales, if you look at these features, for example, you can look at the length and width of these little blobs, white blobs, and you can see that you can have basically very large blobs and very small blobs and thin and long ones. So if a little bit idealized form, this would maybe something like this, where I can put in a uniform background. One background is one conductivity. I can throw high conductivity features. They can be like channels, long and thin, that has a very short width and a long. So this channel will have two scales, its length and its width. But if I start throwing many of this, so basically I have the channels of a small width and different length, I will be covering many scales. And this is somewhat what we will deal with a lot of time. But in fact, this is a little bit idealized. They usually come from some distribution. So if I start throwing small fractures, small high conductivity elements, ellipses, then they start intersecting each other and forming this long channel. So it's basically as a result of this. And then the methods we develop would like them to work actually for problems like this, where we don't have the clear channel, clear inclusion. These multi-scale fields that I showed you in this talk, they basically will enter into the PDE as a coefficient. And the models, these are some example models. So I will have this multi-scale field that I showed you before. So they basically will be, say, diffusion coefficient, or it can be, for example, here at the Brakeman equation, this is, it can be the coefficient, which is basically represents the media properties, can be a convection, oscillatory convection. So basically convection is heterogeneous, so it can be a wave equation, it can be elasticity, or it can arise in nonlinearity. So the problems I will look at, all this multi-scale, will basically, I'm not interested just to look at a multi-scale function, try to extract something, but they usually, in the talks, in these problems I consider, they're basically some type of the coefficients, like input coefficient. And this results to what I call fine scale model, fine scale operator, multi-scale operator, L epsilon u equal F, that we'd like to solve and with some using some reduced model. What I mean by reduced model, so I have this equation that L epsilon u equal F, that we say diffusion coefficient, very oscillatory, or can be something else. And then we have some input. These are the boundary conditions, say source term. So we'd like to find a reduced model. We call it L star u equal F, such that if I use this boundary condition and right-hand side, some right-hand side, and solve this very highly heterogeneous problem that I showed you, and then solve the reduced problem, I can basically get similar outputs. So this is what we're interested in developing such model. One example, this is just to put an aside, where I'm really interested in this multi-scale reduced order model, where particularly this reduced order model used many times, over and over. So this is, for example, an example where in optimization, if I'm optimizing well location in an oil field, I'd like to figure out, so I have the wells, not location, so I have the wells, I'm trying to find what are the pressures I should put in these wells, so that I increase some output. In this case, basically, you start with some initial well configuration, then you run your forward model, right? And then you run some adjoint model, find the gradient, come back and change. So this is typically a loop, and this part is expensive, and you're doing it over and over, right? Because each time you change the same medium running it through, and it's expensive. But this is basically, if we can replace this with a reduced model, this is where we will have a lot of computational saving. So I mentioned in the beginning that I'm interested in this local multi-scale model. So So the reduced model that basically I will divide into two categories for this talk. There will be local and global. So local one, here I will distinguish between approaches that I call numerical homogenization, which I will mention in a second what it is. But in general, the idea of local approach, I have this multi-scale media, multi-scale domain with a multiple scale. I divide it into some grid, some computational grid, where each grid contains a lot of heterogeneity, a lot of small scale, but it's still a computational grid. And in this grid, we'd like to basically come up with a reduced order model. So this is what I will refer to local. So it's done locally in some computational domain. When I talk about global, this is when basically the approaches such as POD and so on, you do some global snapshot and try to find the best subscript. So among these local methods, I will distinguish two. One is the numerical homogenization, where we actually try to upscale, find the media properties. For example, if this is my diffusion coefficient, then I have a coarse grid. I like to find new diffusion coefficient on this coarse grid. And approaches which I will focus, and I say why I'm interested in this, basically try to work directly in a solution space locally. They are multi-scale approaches. I won't talk about global approaches and then how they compete. So mostly I work with a local, because global approaches have a lot of their own advantages. They can really achieve this low dimensional structure a little bit better, but then local approaches have their own advantages, that you have an adaptivity. For example, if you have some France, something entering, you can always go and change. So they're less rigid in terms of computation. So I will start with basically just in a couple of slides, just talk about the numerical homogenization, and just start with the homogenization from the numerical point of view. Let's say that I have this diffusion coefficient that varies in two scales. So this is diffusion coefficient varies in x and x over epsilon. So there's two scales, 1 and epsilon. I'd like to solve this problem f. So I assume this k is periodic with respect to second variable, this x over epsilon, which I call y. Y is x over epsilon. It can be shown that actually this solution u can be approximated by this u hat, which looks like this. It has very smooth part, u0 plus epsilon times some function which depends on x and y. This is y. When I say y, this is x over epsilon. It's not a second variable, it's just x over epsilon times gradient of x u0. So this term may look small, but this is not really a small term, because if you take a derivative, it's order 1. If you take second derivative, it becomes bigger. So this is really, it's small in a basically in L2 sense. So here nxy solve this local problem. So if I look at this numerically, basically I have my global domain. I divide it into my computational grid. This is a coarse grid, this dashed line. So in each coarse grid I have this little period. So coarse grid size, of course, bigger than this epsilon. And in this little domain that I rescale to size 1, I solve this local problem n. And once I know the n, I basically can find u0 also. I take this portion, this whole thing that is on the divergence, and take it average over the same period. That gives me k star for each point. And then I can solve the macroscopic equation. I get the u0, I plug it in, and I have this u hat, which approximates this. This is a well-known homogenization, and you can show that this u is close to u hat in basically in derivative. But what is really I'm interested here, it says that this formula says that in each coarse region, now if I go to this coarse region, I take the derivative of this function. This is u hat function, I take derivative. So this means that I take derivative of this. It's here. When I take derivative of this, so if I take derivative with respect to first x, I still have this epsilon, that's a lower order term. Then I take the derivative of this x over epsilon. This epsilon comes and eliminate this epsilon, so I have this term here, grad yn. Right, so where I take the derivative with respect to this and grad x, and there's one more when I take the derivative of u, but that's also an epsilon. So in the leading order, this derivative has this form. I can take grad x out and I call it xi, so I have this expression here. Right? This is the same. Actually, this is equality. Sorry. So grad x u0, in fact, in each block, since u0 is a smooth function, grad x u0 can be assumed to be constant, right? It's a, if I'm doing some lower defined element, this is a constant. So basically what this tells me that this u epsilon in this domain has roughly 2 degrees of freedom. If I know the n, basically this has very low dimensional structure, because this n, if I know the n, is basically this function has 2 degrees of freedom. This is also true if I go to not necessarily periodic case, for example, some more general cases when you have the K is a homogeneous ergodic field, then basically it's this representative volume that we call it, this is representative volume. This representative volume has to be much bigger so that it contains a lot of scales. And this periodic boundary condition is not necessary, but you can basically also argue that the solution has this very low dimensional representation within each coarse element. And in fact, often this method is used in even in a more what I call in a numerical homogeneous upscaling setting. So you take your fine grid, so this is a grid where your permeability is given, coefficient given, you divide it into the coarse grid, and then you want to compute effective K star, this effective coefficient for this block, one homogeneous coefficient for this block. So you take this block out, you solve 2 problems from, so this is a underlying problem with 0 right hand side, but the x1 boundary condition. So x1 means that the flow going this way. So this is x equal x1, x2. And then you solve the same problem with x2 boundary condition. And then you can compute the K star. So this is even like more, you can just generalize. This is actually very frequently used in for example, in subsurface industry. And you can even go further. You can assume that you can even like take this block. So now what we did, we take this coarse block, we're basically probing it with 2 different boundary conditions. You can take the coarse block here and probe it with multiple boundary conditions. Let's say I call it BI. So I solve this local problem with number of boundary conditions. Then if I want to find K stars, then I assume this block has homogeneous properties and I solve it again with the same boundary condition. Then I try to match some average responses. And this basically will give you definitions like this, and this is another way you can think of where this coefficient coming from. Now, the thing here that all these approaches, when you compute K star, it's basically, this assumes that solution represented with very few, like 2 degrees of freedom, or very few degrees of freedom. And this is typically true for many of this homogenization, and or even like if you go problems like we have Darcy-Stokes, when you basically have these effective properties. So there are only a few numbers you're computing, so basically you just need a few local fields. Right? There's this underlying assumption always that you have these features, solution features in this part of the domain, you only represent them with very limited number of, has very low dimensional structure. In fact, it has, like, if I look at the K star, right? K star has 3 values. It's a symmetric tensor, so it can have 3 values. So basically, there's always this restriction there's an assumption that the local solution space represented with very few degrees of freedom. And this is usually not true in general. So in other words, if I don't have scale separation, I need actually more features. I can't just assume that this solution space in this local domain can be only represented with 2 degrees of freedom. And to show you, this is illustrative example I like to show. So if I have a coarse block like this, and I have a small, this is a block, it has to say background conductivity 1, and I have the high conductivity inclusions like this. So this is nice for the homogenization. In other words, this can be represented if I solve this problem twice, left to right, bottom to top. I can use this for any other right-hand side. So I can write solutions as a linear combination of this. But on the other hand, if I have say the same coarse block but cut through 3 high conductivity channels, I cannot do that. This is not hard to see. For example, so let's say that I am going to solve this problem once. So if I have a 1 basis function, one solution space has say 1 degrees of freedom, and if I solve this local solution, and I have some flux. So I usually solve this local problem subject to some boundary condition, and I'm going to have some fluxes inside this channel. So channels, since they're high conductivity, they basically will separate from each other. Let's say I have when I solve it, I will have a flux 1 here, 2 here, 4 here. So what will happen that my flux is correlated, right? So if flux is 10 here, associated with 20 here, 40 here. But this channel goes on a boundary, it can be far away from each other, and I can put any value. So basically if you give me one basis function, I can always find the coarse boundary conditions so that this basis function will not work. So this basically actually says that features like this, you have to have it separate. And in fact, you can have many channels like this. And this is what we want to do. We want to find this reduced dimensional representation. And we will use the multiscale finite element concept in a sense that we're going to try to build finite element bases that have the information and try to find some minimum number of them, or just try, at this point we'll try to actually develop some framework how to build these things. And this is one way we will basically generalize the numerical homogenization concept, because we need more and sometimes we need more degrees of freedom. And this is also a little bit this goes back actually when we were working with preconditioners and trying to find optimal preconditioners and coarse spaces. So a lot of these things actually started there. So let me just say a few things about multiscale finite element, just as it proposed by Tom Ha and Wu. Actually, it goes back to Babushka and Osborne, right? First to come up with oscillatory basis function. So I have the domain, my domain, and I have a fine grid. So when I say fine grid, basically it's a grid where my properties are single value defined. So in each block I have the homogeneous, this little fine block, so it resolves all the fine scale features. And then I overlay the coarse grid. So this is called coarse grid. These coarse lines are the coarse grid. So each coarse grid consists of agglomeration of the fine grid, connected union of the fine grid blocks. And my solution on a fine grid has this representation, right? UI, phi. Phi's are usual hat functions by linear UI, the values at this fine node. And what I'd like to find is the basis function phi, such that this U star approximate U accurately. So goal is to find phi. So one very first phi that you can think of is the following. I can take my bilinear function, which is 1 here, 0, 0, 0 along here. So I just keep the linearity along the edges and just solve the local problem inside each coarse grid, like this coarse grid. So here we have a 4 coarse grid blocks. So in each side, each coarse grid block, I'm going to solve the problem. So it's described here. So I have the linear boundary, but inside I solve the local problem. So LK phi is 0 inside each this things, and on a boundary on this cross it's equal, and outside it's equal phi 0. Okay? So this is just the oscillator hat function, and then you just do the Galerkin. So you just write the solution as a linear combination, plug it in, and multiply by a test function. So you can actually, the grid here doesn't have to be structured. You can do this in any grid. So this approach with one basis function, you can show that it's actually similar to the numerical homogenization I showed. Because having one basis function or having 2 degrees of freedom just to define this effective property, they're basically similar. And one thing you immediately face in this problem, that this linear boundary condition gives a problem. So to show just this, I look at this problem just to show that this linear boundary condition really can give large errors. So here I have these are red that you see, this is high conductivity regions, and the background is 1. This is conductivity is 1. So I solve, this is how solution look like. If I look at this solution along this line, this is my 3 by 3 coarse grid. Along this line, you can see that it's basically, it has a non-linear behavior, not linear behavior. Well, if I use the basis function I described before, which are linear along here, when I generate a multi-scale solution, it will be linear. So it will miss the features along the edges, totally. And if I go to the multi-scale problem I described before, solution inside will oscillate, right? here oscillate, and I'm replacing it by the linear function. So this gives me errors like this. These are quite a bit studied in the literature. So errors goes as epsilon small scale over h, which says that if I'm in a periodic setting, I have to take h much bigger. So this led to develop oversampling, and I need this concepts I'm going to use later. So oversampling, basically, how can we actually get rid of this linear boundary condition effect? Because solution is not linear, so we want something that looks like solution along the coarse boundary. So if I have on this coarse edge k, if this is coarse element k, if I like to build a basis function here, I basically will solve the local problem in a slightly larger domain S, this oversampled domain S, and then I basically throw away everything between S and K and use only internal information to build a basis function. So phi j over sample, basically these are 4 basis functions in this large domain with 1, 0, 0. I take their linear combination, and then, for example, I take my basis to be 1, 0, 0, and these are my basis. This method still can have large errors. And a question I'm interested in right now, how can we enrich this basis in a systematic way? And how to use ideas like this, you'll see how it will come in oversampling method. So this is actually, it goes back to this method that we were working with domain decomposition. We were developing spectral approaches, but then when I try to apply it to different mixed or other formulation or solve problem, I find that they're very rigid. So this led basically to think that to have some type of framework where we can actually try to have a just general multiscale, local multiscale method. So let's say that I have this example, but we have generalized this many different equations now. So I have an equation, I write divergence x mu, so it may have a parameter, but in this talk actually I'm not gonna, I will just say one short slide what we'll do with a parameter, but in general there won't be any parameter. And so I look at this problem as I have some input. So input in this case will be my source term, my boundary condition, and this parameter. This is my input space. This is my forward problem, right? And I have an output. So this method, generalized multiscale find element, divide, so just follow, and these are actually reduced basis, many other approaches use that. So we divide the computation into 2 parts, offline and online. So in offline part, basically we cannot touch any input. So this input parameter, which was a source term, boundary condition, parameter, we don't involve in this state any of them. So we start with a coarse grid. So there's 2 things in this. So we overlay coarse grid. We have a coarse grid. It may be given from another equation. And then for each coarse region, there's really 2 things which I will here describe, and that's what we need. One is that we compute snapshots. Snapshot is a functions that represent how solution will look like in that coarse region, without actually trying to solve a big solution, the global problem. And once we have this snapshot, we will do some spectral decomposition in this space of snapshot to compute the multiscale basis, what we call offline space. So if we have a parameter, then an online stage, we get a parameter right-hand side boundary condition. So if we have a parameter, so which means that we have a new coefficient coming, so we have to compute new basis function. Basically, we're going to we'll compute them in this space. But as I say, I will consider no parameter independent case. In this case, basically, given a right-hand side, I have my space, I will solve the coarse grid problem. So I will start first explain what's a snapshot space and how we compute it here. So basically, if I look at my global problem and run my solution across the input space, so these are long vectors, and I look at these vectors in this region. So what I like to do, try to find some vectors that represent this space with some some accuracy that I can estimate. So that's the first approach. For this, I will list just few snapshot spaces. So it's a very simple snapshot space. In fact, the one we used before, it's just a all fine grid vector. So if I'm in this omega I, this region I call omega I, this is union of 4 coarse blocks that share common vertex. I can take all possible fine grid vectors, another 1, 0, 0, 0, 1, 0, 0, all possible unit vectors. So this is a very simple space. I don't have to do anything. This can be my snapshot space. This is one of them. But typically, we work with a little bit different snapshot space, but this is including. So often we work with a snapshot space that are harmonic extensions of something. So in this particular case, this is also widely used in various areas. So I can actually, I go along the boundaries for every node. I have a 1, put 0 everywhere else, and solve the local problem. And go around and basically solve for every node. So this is expensive to compute, but this is then it can make the further calculation cheaper. But this is another snapshot space, and you can. One thing about this snapshot space, you can basically, in this case, we are assuming your solution can take any values on a boundary, right? And you know what the difference between solution solved with some right hand side and an interpolant from here. So we are often interested in this oversampling, and so you can actually go to larger domains, which I will tell you why later. So we'll go larger domain. One of the reasons, maybe I just go. Let me say later. So you can go to oversample domain and basically do the same thing, right? You can put harmonic extensions of the unit vector. So you put 1, and you just put source every node and solve the local problem. Or actually, these are another ones which I will comment later. You can, in fact, you can just take some random vectors along the boundary. Just Gaussian random vectors along this boundary. Okay? So you solve the local problem in oversample domain, and on the boundary I will put some random uncorrelated field on the boundary. And then snapshot space in this case will be basically restriction of this field in this domain. I will explain why this snapshot later, once I describe this offline space. So once I have the snapshot space, as I mentioned, we go to the offline space, and these things are connected. So that's why I want to say this and then comment on that. So what is an offline? So an offline space, we basically would like to find a subspace of snapshot space, and using some basically some bilinear form. So we're doing we want to do some spectral decomposition in offline space, in a snapshot space. So this is a snapshot vector. So we'll do some spectral decomposition, and to do the spectral decomposition, we need some bilinear form. Here simply it's written generalized eigenvalue problem with two right and left and right norms, M and A. Right? This is what we need. And where this M and A typically comes from, so these are usually come from the analysis. So when we try to analyze the method, so if we have take a look in another discretization, we have a U minus U0, we divide it locally into the regions, and then we have some norm there. It could be say H1 norm plus some jump term, for example, if we're doing DG, or I will show you, for example, for mixed method, we have another term, and we want to estimate it by another term, right, by another norm. So we have to be careful because these solutions are not smooth, right? The expansion I showed you before, if you remember, we differentiate that solution twice. It's very large. So, for example, we don't want to go to second derivatives and so on. And second, we want to make sure these eigenvalues decay very fast, right? This is also very important. And this is where a lot of oversampling comes, and make sure these eigenvalues decay very fast. Because if we don't have it, then we can actually just get a lot of basis function, because to reach accuracy delta, I need a lot of basis function. And so this is basically just the abstract way to write it, but usually computationally this is all you do. You take your snapshot, you put it in a column of a matrix, you call it R snap. For example, if I had the choice 1 where we used the unit vectors, then R snap is just identity matrix, right? And then we take this is actually one example, for example, for the elliptic equation. For example, this A is my stiffness matrix, I take my stiffness matrix on local on a fine grid, I multiply from the left to this R snap on the left, on the right to R snap, and the same, I take my mass matrix with a special modified coefficient, which I will say in a minute what, and then solve this eigenvalue problem, and then pick the dominant node. And this is the offline space. So now I just want to give you some intuition. Why? I mean, what do we have to really watch? Because one thing we really want to have a very few degrees of freedom, for example. We want to be these methods to get only 2 degrees of freedom if we, without knowing we're in a homogenization regime, right? If we have a underlying heterogeneity as scale separation, I mean, I don't want to have too many basis functions, right? So here's some just examples to emphasize that this eigenvalue, choice of eigenvalue problem, matrices M and A, those bilinear forms are important. So here I just will work with the snapshots that are unit vectors. So on each omega I will solve the eigenvalue problem, divergence k grad psi I equal lambda I k tilde psi I, where k tilde is computed by taking some function. So I have this is a multiscale function, a bilinear function on every node. I take k grad phi I square point-wise and compute this k tilde and I put it here. And so what is the, let's look at this for the 2 choices. If I have a multiscale function as a phi, or I use a bilinear function. So if I use bilinear functions here, phi, then this k tilde will look like k. I'm going to just take one coarse block like this that has 4 inclusions, 1, 2, 3, 4. So inclusion is an isolated high conductivity region that doesn't touch the boundary, and that 2 channels, right? So then we can solve this eigenvalue. We solve this eigenvalue problem with this. If I put a k, then I get an ordered eigenvalue. So you can actually show that. You can show that in this case you will have 6 small eigenvalues, very small. They will be as small as an inverse of this high conductivity field. And our convergence rate in this multi-scale methods will go as a 1 over lambda. And you can actually easily show that by just looking at a Rayleigh equation. Well, if I use multi-scale basis function, then basically this k tilde, when you look at the k tilde, it won't have this inclusion, it will have just 2 channels. So there will be only 2 small eigenvalues. And this is really important for us because if we have many inclusions, we don't want to generate basis function for all of them. We want to just generate basis function for. And then we basically, and this is what I mentioned, the convergence rate is one of the eigenvalues that we did not include. Let me skip. So if you have a parameter, you have to do one more. You solve the, for some mu I, you solve offline, and then for parameter dependent, you basically select mu I and then do the procedure I described, and then in online stage do new one. But I'm gonna just skip this and just show you one, for example, this method in a mix version. So one also good reason having this snapshot, it's not just to get a high accuracy using few bases. We can get a high accuracy. Also, it can be very useful, for example, if we want to have a mass conservation. In this case, so if I have a mix, if I'm going to do the mixed version of the multi-scale method, so I write the problem in a mixed form. So there's a V and P, 2 separate. Now you treat them as a separate. For P, we will use a piecewise constant basis function. For V, we're going to generate the basis function. So what will be the snapshot in this case? So snapshot in this case, we basically solve this. We'll solve the local problem. We'll put a 0 Neumann boundary condition here. So we're going to just try to get all possible velocities along this edge. And to get this, it's not hard. You just put 1 all over 0, then 0, 1, and so on. Right? You put all the possible 1. You put flux 1 here, 0, and then 0 and 1 in the next grid, and so on. But since it's 0 Neumann here, so you need to do something with a divergence, and you select that constant that is a compatibility condition satisfied. So these are the snapshots. This is what's described here. So you solve the problem, and Vj at mi is the normal. This is equal. And then once you have this snapshot, And then the eigenvalue problem, and this is from analysis, so it looks like this. So this matrix A will be, M will be my usual, basically this is basically energy norm. This is K minus 1 VW. Remember V and W is a velocity. Well, the A will be a jumps in the pressures. And then you select the dominant modes and you build this basis. You build an offline space. And let me show you how this method works. So here's an example. So we look at this is 200 by 200 field, and we have a high conductivity channel inclusions here, mixture of channel and inclusion. And here's an error in V in K minus 1 V square norm. So if I pick only 2 bases per edge, so original edge has 20 bases. If I pick only 2, basically error is about 6%. If I pick 3, the error goes down. Because error will stop here at some point because we use this harmonic extension, but if we get here, the error is small. And we use this particular for the multi-phase flow transport. So if I have a 2-phase flow of oil, water displacing oil, the equations have this form. So we have a pressure equation, which is just like before, except there's a lambda S. Well, S follows hyperbolic, it's a hyperbolic equation. So in this case, if you think about it, if you're solving saturation, this S called saturation, P called pressure. So if I solve saturation in time, each time plug it in, I'm solving pressure equation over and over and over. Right? So here, what we do, initially we generate multi-scale basis function just by ignoring lambda S, and then going to see how it works. So this is a lot of computational solving because equations solve over and over. And here's basically you inject from the top, produce from the bottom. So here's a solution snapshot at 3 different times. This is if you use 2 bases and you use 4. You can see that there's quite a bit gain when you go, for example, to 4 bases. So just one comment in oversampling in general. Why is it really important? So if we go back to this or the previous what I discussed. So along this edge, I assume that solution can have any values, right? But this is a bit overkill because, for example, I know that my solution is a harmonic function, right? So it can't really take any values. It has some smoothness property. So by imposing this type of actually snapshot space, in fact, this may not work in a homogenization setup because you may not get just 2 basis function that 1 basis per edge give you the same error as you get from the homogenization. So to do oversampling or to get very small snapshot space, what you can do, you can basically go to this small region around the edge and generate harmonic functions and take the restriction and then from there you can do some type of local eigenvalue problem, and you can actually show that this is where you can get much fewer basis functions and more accuracy. Here's a little bit of explanation, basically why oversampling really useful, because if you look at the solution inside, if you have a scale separation, right, basically you'll see that a lot of these U0s away from the boundary, they won't see the oscillations, right? So you're basically dealing with this in this case. This is some table just shows how oversampling versus not oversampling, and you can see that if I use oversampling and I have 1 degree for freedom per edge, so that oversampling is much better than not oversampling. But later on, actually, not oversampling also is accurate. So this method, in fact, need some adaptivity, otherwise they are not very efficient. So adaptivity means that we actually have to define some error indicators and which tells us where to add more basis function. Right? And this is what we did in one of our work with my collaborators. So this idea, basically it follows a usual error indicator strategy. So we have a L2 H-1 indicators, but we need to rescale them with an eigenvalue. So this is what's the only key. And then in each region, we define some type of an error indicator. That is, you take the residual, you take it L2 norm, and then you multiply it by the eigenvalues that you did not include. and this is your eta i's, and then you select the largest 70% or so, and basically at the basis where the error is large. And you can actually show some estimate, and this is what we did. And these methods work. Here's some errors. For example, we can show that this is uniform, and this is. One more thing before I finish. So this snapshot calculation can be expensive, as you see, you notice. For example, especially if I'm doing this oversampling, right? Because I have to do harmonic extension every unit vector. So here we use these ideas of randomized. This actually come from the randomized PODs. So for example, if I like to compute n bases, all I need to do is just take n plus 4, in this case, n plus 4 random boundary conditions. So we take n plus 4 snapshots. For example, if I want to compute only three bases, I take 7 snapshots by selecting random boundary conditions and then extending them. And these are my snapshots. Then in that space of 7 snapshots, we do the eigenvalue problem and select the 4 eigenvectors. And these are the basically table that shows if we use all the snapshots and we use randomized snapshots. And this is a fraction of the basically snapshots. So randomized is 7, say all is so many. Like this is a fraction of the number of randomized snapshots. This is basically computational saving. And these are the comparison of the errors. We can also show actually similar convergence rate here, because of using these randomized POD type ideas is a little bit modified. And these are also work well with adaptivity, because if I want to add one basis function, all I need just to generate 4 new snapshots and basically take the components out of the first basis, take the components out, and then do the eigenvalue problem. We have applied this to various problems, and just want to mention a few. So for example, we use this for wave equation. This is a work with a geophysicist and Aramco. We're trying to use this to speed up the seismic wave simulation and inversion, both acoustic and elastic. Like for Brinkmann, we have used this for the uncertainty quantification. Also in nonlinear problems, we have actually extended these approaches to nonlinear function. Particularly, there's one issue with how rapidly to estimate nonlinear response. Because if you have a reduced dimensional representation of the solution, the response, when you estimate the f of u has a reduced dimension, you want to do this f of u estimation without touching the fine grid. So these are something we have also extended, and also more from the modeling point of view, how we can actually use for example, approaches such as if you know dual permeability, and so how can we use this type of approaches to replace, for example, dual permeability. I'm going to actually just finish with this. So I talked about the local multiscale methods, because the concept of generalized multiscale, where we mostly work to design this snapshot space and offline space. So these are somehow interrelated, how to get fast convergence. And then we have used this in a framework of, say, mix, this continuous Galarkin now, and also applied for various problems. I'd like to also thank my collaborators. Thank you.
Yalchin, did you try to compute for problems with oscillating boundary conditions? Because there it should be much more subtle, right? I mean, things depend on angles and number theory and stuff.
Not oscillator, but we try to, for example, look at a problem like interface problem. If you have a homogeneous and non-homogeneous, it's like at the interface, in a sense, if I remove the top, it's like you have a stock stars. If you remove the top, the solution is oscillator. So it's basically all it means that you need more basis function where you have those oscillations. And this is, so if you look at the problem, it's
It depends on sort of, if you think of a polygonal boundary, it depends on the angles and stuff. So it would be interesting to see what the method does.
No, but I meant that if it's inside the domain we have worked, and that basically actually we show that that shows you can see that away you basically have one basis. That is homogenization regime, but inside you have many bases because you're trying to represent this region.
The binomial basis can be used to instead by some other basis where you can read the wavelength that this kind of things basis. And maybe improve the accuracy. Because some the positive accuracy, the order is 2, but the 2 maybe use the one or the smooth basis maybe can.
No, I think smoothness here.
Can you increase the accuracy?
These are the you don't want a smooth basis here, right? Because solution.
Yeah. I also that this is binomial. We also use this.
You need basis to match to the.
Yeah, maybe improve the country do not have the error analysis. Still do not get the theoretical analysis of the error. So maybe you use some other basis, maybe improve the error. Improve the accuracy, not improve the error. Currently, because you use for the image processing, use the read rate or curve rate or wave rate is kind of a generalized wave rate, and improve the appearance of the image. And then use this kind of things. And maybe and then you improve the accuracy.
Yeah, I mean, I think I don't know. We can talk about later. I think wavelength probably.
Of course, this is related to some recursion function estimation or some emission processing in this area. And then we also use this to compute some solution.
We can talk later. Any
Yeah.
other questions? Okay, if not, this is the last. Thank you.